So this is the last section. This talks about the Goldstone Apple Valley Radio Telescope, and specifically the Seti project, which is the search for extraterrestrial intelligence. So to do this, there's several videos. 1, 2, 3, 4 explains the whole project, and there's some information here on the intro, and we'll look at it briefly. Okay, it explains how they're trying to figure this thing out and the statistical probability of running into something. Okay, and it talks about what the telescope does. It actually scans back and forth in a small patch of the sky. Okay, and it's looking for anomalies and signals. Okay, there's going to be signals that are really, really strong. That's just background radio interference. We don't care about that. We're looking at small little blips that don't last that long. We consider that an anomaly, and if they keep showing up, we maybe consider some kind of intelligent life trying to transmit amongst us. All right, but let's talk about this part. Assume every star galaxy has planets and that intelligent life begins in every planetary system. Assume all civilizations eventually try to send a signal to our direction. Let's assume that all of the billion years, a typical civilization almost radio signal us for about 1,000 years. Well, that's pretty crazy, right? We've only been using radio on Earth for about 100 years, and it's 4.5 billion years since Earth formed, so it's probably a completely optimistic assumption, right? If you put all those numbers together, you conclude that for our optimistic scenario, one star in a million should be sending a signal in our direction. Those seem like pretty long odds, especially optimistically, but there's 100 billion stars in our galaxy, so 1 in a million stars would be 100,000 stars sending us a signal. So this is the whole numbers game, okay? So we're going to look at all this when you're doing this. So this is an interesting read, okay? To go back into this thing, let's look at what the wavelengths are, okay? So we're looking at megahertz, and it's going from 0 to 200 megahertz, okay? To kind of understand what this thing looks like, this gives you a bunch of notes on it. So this is the atmosphere, right? Here's gamma radiation, X-ray, ultraviolet ray, visible light spectrums here, infrared, microwave, radio waves. Okay, this is radio waves is the window which they're looking at for this information. They're very, very long wavelengths. They travel very, very long distances between crest to crest, all right? So that's kind of the range we're looking at for doing all this stuff, okay? So this is a neat little table, but for all practical reasons, where the radio wave frequencies are down here. And FM radio is probably one most people know, like 98 megahertz or whatever it is. We're looking about from 0 to 200 megahertz is the interest area of the signal, right? So 1,000 megahertz is a ton of, it's like a gigahertz, but we're not in there. That's like our cell phone signals are in that range. Okay, so we're 5G. That means 5 gigahertz, 4 gigahertz. We're not there. We're megahertz. So this is radio waves. Okay, so this is the window that we're looking at to find the frequency for our noise, galactic noise continuums down here. And then the idea behind it is like this really small range that they're trying to detect some signals from that are what we're looking at. So we're going to go back one, and here's an example of an interesting thing called the inverse square law. Let's say there's a planet way out in the middle of nowhere sending a signal, okay? And if you're close enough, you would get the entire signal. As far as a can of spray paint is probably the easiest way to think about it. The further you back out, the less the paint's going to hit, let's say, the barn or the piece of wood you're holding up. The further away you get, this inverse square law, it takes more energy to send it further away because you're trying to cover more space with the same signal. So every time you double the distance, like this goes from x to 2x, it's 1/4 the amount of power that's coming out that way. Now it's 3 times, it's 1/9, and if it's 4 times, it's 1/16. This plays a factor with radio waves because they get diluted essentially as they're being transmitted. So here's another example of that is here's a flashlight. It's pretty brilliant when you're sitting up close. It's shooting in your eyes. But the further you get back, like this is 6 meters. 6 meters is probably almost 20 feet, right? It's way less as far as the amount of power that's hitting you. So it's a way of kind of looking at the signal. If this is a planet, by the time it gets to us, it's a Weebot. So kind of an interesting way of putting it together. So we go to find a signal in this, okay? We try to find a signal. It's going to be kind of hard, okay? So this is set up for high school kids to kind of do this. This guy put the project together, and it's actually kind of fun. And what you're going to do is you're going to search through Seti data and try to find something that makes sense. Okay, when you say makes sense, it can't be a long nonstop signal. That we consider just radio frequency interference, RFI. But what we're really looking for is like a signal that's short, it's intermittent, lasts a few seconds, and we consider that a possible thing. All right. So this is what a waterfall plot looks like. Okay, here we have right here is the amount of time, and this is the megahertz along the bottom. Right. This is 1,000,000 hertz. So it goes from 0 all the way up to 220 megahertz, right? And this is a telescope scan of 10 minutes, right? 10-minute lengths for 60 minutes. So it's going back and forth, back and forth, back and forth, all right, for an hour, right? So what happens is, like, you'll see these long bands. We don't care about the long bands. We want the short little ones. Like that may be a real signal. I mean, this is artificial, it's just drawn from an extraterrestrial source. So this is our interest, these short little spots, almost like SOS dots down the center of this thing, okay? So this is kind of an interesting way of kind of looking at it. Like, this is a more blown up example of what something looks like. All this stuff, some of these bands, this is just radio frequency interference from the cosmos, and they're always on, so it doesn't really count. We don't really care about that. But what we do in the thing is we try to eliminate pieces that we don't want and blow up things we do want. Like, if you keep cutting back more and more of the things in the background, and I'll show you how to do this, you'll eventually isolate individual signals that are pronounced in the background, okay? Eventually, if you get this thing buzzed down, and here's a small range, you can cut the range of this down. This is from 103 megahertz to 104 megahertz. I'll show you how to do that. And then eventually, you isolate the very, very important things. Like this one, all of a sudden, it has a strong signal that's going, and this is the time interval from 236 to 244 seconds. There is a blip. What that blip means, no one knows, but you mark it down. That's what essentially you're going to be doing. And a lot of times you'll see this. This guy keeps getting it tighter and tighter on the frequency, 40 to 50. The time is smaller. He's trying to make it blow up. And look at this. And as you get this thing tighter and tighter, it's going to tell you what you want to know as far as, is that a real signal or is it not? Okay? So the best thing to do is, this kind of goes off the whole thing with another explanation. We're looking for these little dots. That tells us something. All right? So what I'm going to do is, last thing I'm going to do is show you this worksheet. Okay? Worksheet is, you're going to talk about this to this. What was the starting frequency? The ending frequency. This is RFI data, okay? Radio frequency data, right? The interference. And then you're going to talk about instrumental noise. So I'll show you, when you work this thing out, how to fill all these things out, because you have to take out these. What are the bands you take out? This is the bands you saw that are interesting, and how long are they visible on the spectrum, okay? So this is how it's done. You put the school name, or obviously the Salisbury School, Dewick will be the teacher, and we'll put the date. And obviously they want to see if they keep seeing some things keep popping up again and again. They call it real, and then they go back and really, really look at it, and this tells them that these things are important. So, and possible signal from extraterrestrial life.